function. It's a mathematical operator that produces something if you give it some input. And these becomes the outputs of these neurons, and then they are again combined with some kind of linear combination of these weights, and then they are fed to another set of neurons. So how many of these layers of neurons you have is called layers. So the more you have, more than 2 is already called deep learning. And the way to work with it is to fit your input and output data by finding these weights. This is all any deep learning or any machine learning algorithm does. It tries to find these parameters, which are these weights. The way to do it, of course, it's clearly an optimization problem. You want to fit, it's a curve fitting problem. You want to fit some inputs with some outputs. And you want to perturb your parameters, which are these ones, to get the good fit. So you're recursively trying to minimize the gap between the outputs, and that is an optimization problem, and it finally comes down to something called linear algebra. So here you can relate this equation by trying to find the change in the parameters so that you get a little better improvement in your output matching. So recursively you will be doing that. So this equation is kind of the workhorse, where x is kind of the delta parameters. And the very recent developments in this field is in optimization, of course, and many algorithms have been developed because this equation will be solved many times, because we talk about training when we talk about machine learning, and training is essentially finding the parameters, and there how efficient this equation can be solved is the crux of the matter. And there stochastic gradient descent has evolved as a very important tool, a very important algorithm. But what is machine learning's aspect that is of interest to control engineering or control technology? Well, machine learning does modeling, clearly. With the use of those models, it predicts certain things, and then based on those predictions, you make certain decisions. Simply can be said like that. So where does the interest really lie? Is machine learning enabling technology? Is it letting us do things which we couldn't do before? Or is it also improving the current control technology, certain things that we struggle with the traditional control? Well, typically speaking, machine learning has evolved with certain domains. Control of robots or drones, it's clearly decision making where we are evolving, starting to see that control of robots is always most likely a machine learning driven system. Speech processing like Siri or Google Voice or whatever, which predicts your voice or predicts what you're saying. You ask, hey Siri, can you tell me how many restaurants, or I want to go to this sort of a restaurant in the neighborhood, and it just recognizes that, goes to Google, finds it, and comes back with some solution. And one really important achievement is computer vision. This is where we can predict things as if the computer has eyes. So the way it does it is you throw in thousands of pictures of different things like animals, dogs, cats, oranges, and so on, and you label them. And the input is those figures, and output is those labels. And then it learns through this training and finds out these parameters, or whichever way it does it. And then you show a new picture of a dog, and then it points out, I'm 95% sure this is a dog. So that's very important, specifically thinking about self-driving cars, because that's an evolving, emerging industry. But if you look at machine learning, and I went to this website to learn a little bit, and then I found like there are hundreds of things going on. Computational learning theory, Bayesian learning, deep learning, kernel, you name it. But the thing that is of most importance to control engineers is reinforcement learning. This is like the control theory of artificial intelligence domain. So this is something that we need to pay a little more attention as control engineers. But what exactly is reinforcement learning? Well, reinforcement learning comes from behavioral psychology. And behavioral psychology works on humans, and it has been tried on animals like dogs. Let's say you have a dog at home and you want it to shake hands with you because you like the dog to do that. And so the dog comes over and tries to shake hand with you, and you shake hand with the dog, and every time it successfully shakes hands with you, you give him a treat. And the dog associates that there is a value associated with this shaking of hand, and then it learns that it needs to do that. So machines are no different. We develop the machines and we can just kind of train them just like humans or just like dogs or cats, with some value associated with their actions. So reinforcement learning, in a simple definition, is learning best actions based on reward or punishment. So you associate your actions with some rewards or punishment, and then you want to maximize your rewards and minimize your punishment. So it automatically does that. Cue learning is the most commonly used reinforcement learning method that is showing up. I'm not going to discuss any of that, but just a matter of fact. But what is reinforcement learning good for? It's really good for when we have to learn our actions by interacting with the environment. So trial and error is part of reinforcement learning or artificial intelligence-based control. So to give you an analogy, learning at school and learning at the job. Well, reinforcement learning can be divided into model-based reinforcement learning or model-free reinforcement learning, and then it depends on which direction you want to learn things. Whether you want to learn how your outputs are affected by your inputs, so you provide the inputs and you learn how the outputs or values or objective are affected. Now that is in our domain called modeling, or in traditional control it's called system identification, but in the field of artificial intelligence it's starting to be called as supervised learning. But it's the same approach, it's the same thing. So that I would call it learning at school. You learn at school all you want to learn, and then you go and work, use that learning. On the other hand, you have model-free reinforcement learning, where you do the other way around. You supply your outputs and the value function and objective, and then you try to see what to do with that. And that is essentially reinforcement learning. So I would call it learning on job, where you have a customer waiting for you to do something, and then you just have to learn what to do because there is a value at the end. So now I'll talk about a little bit on model-free control, some very prominent methods that I thought are most relevant in this context. And thereafter I will talk a little bit on model-based controls. So PID has been the workhorse of control engineering for decades. And slowly it has been figured out that PID tuning is a complicated issue. The only reason where PID fails is because it's oscillating, the loops are oscillating, and that's because the tuning is poor. And that's where something called intelligent PID came in, where we try to relearn what should be the tunings so that it continues to function optimally. And there are some other methods like extremum seeking control and self-optimizing control, which are more towards the optimization domain or the real-time optimization area, if you remember the topmost layer in the Sigurds hierarchy. Not the topmost, but somewhere towards the top. So PID is a very simple algorithm. To say the least, you have some measurement, let's say the temperature in the room, and you want it to be 25 degrees, and it is not, it is at 20 degrees. So it sees that there is a difference of 5 degrees which it has to, this gap it has to close. So then, if the gap is not closed, then it has to do something. So it goes through an algorithm where it tries to add up certain aspects and changes your heating. And as long as your temperature is not 25, it keeps on doing something. As soon as it reaches 25, it's happy. It doesn't have to make changes. So that's PID demonstrated in a very short way. What is intelligent PID? Well, it is essentially about auto-tuning. Last week, Ostrom was here for a lecture, and I did go through his lecture, and he talks about some relay method, which I don't know anything about, but as I understood, it's about automatic tuning, where you use the data and try to perturb the system with some other signals, and then you figure out what is going on, and that becomes the source of your new tuning. And if it is done automatically, then it becomes auto-tuning. So you don't have a man in the loop trying to influence those tuning decisions. So intelligent PID and model-free control has been a topic which has been a matter of significant interest to this person called Michel Fliess. And I went through some of his articles to understand what he does. But I'm not going to present everything because I didn't understand all. The unknown complex mathematical model is replaced by an ultra-local model. This is what he does. And towards the end, he says that this model is not even something that you need to use in the intelligent PID control. And the main thing that I figured out is this. Our main tool is an online numerical differentiator. This definitely is interesting because when you have an online numerical differentiator, you need to take care of the noise, and they somehow perhaps do it in a nice way, and that gives them some additional information. As I already told, data has all the information, you just need to be able to extract the right information out of it in the right way. As was also presented by the level control problem by Ricard. So Michel Fliess has been working quite a lot on model-free control. I mean, there are many publications, and very recent, all of them in 2018, and has a very good background in this field. Just if you're interested more in this topic. So now I'm going to talk a little bit about model-free control in the RTO domain, where I'm going to talk about extremum seeking control. So let's say this is your bigger objective and this is your decision. So how you use your decision governs where you lie on this manifold. And you want to be here because that's optimal, for example. So the way you do it is you provide a sinusoidal perturbation to your decision. Let's say you're sitting here, this is where you're operating, so you perturb the system, and then it produces a change in your value function or objective function, and you see that the trends are opposite. This was your perturbation and this is just the opposite. And if you do it on the other side, then they are in sync. So if you multiply these two signals, they are going to already give you some information which direction to move. So that's a very smart and nice data-driven approach called extremum seeking control for optimal control. And the only drawback is that it is a local optimizer. For that matter, most of our systems are local optimizer. Now, Sigurd's self-optimizing control. It's also a very interesting control approach where we get rid of the bigger RTO layer, and we say that we take the data, take the measurements, and find a combination of that measurements. If we keep that to constant using a feedback controller like a PID controller, then we can have some inputs to the real system, and it will ensure that the system operates optimally. Beautiful. How he does that? He gives, again, he has wonderful examples, a marathon runner example. So if you're a marathon runner and you're running in Norway, in Trondheim, you are going to come across a lot of hills and troughs, and you're going to have a strategy to address that problem. So how do you do that? What do you control? In your head, you run at the same speed, you're going to exhaust when there's a hill, because you cannot run at the same speed, your heartbeat is going up. And there are several different disturbances. So the best thing to control in a marathon runner example is your heartbeat. So if you're going up, your heartbeat is going up, so you slow down a little bit. If you're going down the hill, then your heartbeat will relax a bit, so you can go a little faster. So that's a very neat example where you choose a measurement which is best suited to optimize the bigger process. Now our